Okay, in this video we want to talk about something called an antiderivative. And we want to see that there is a relationship between an antiderivative and the area under the curve that we were talking about. So let's just start with the simplest maybe example, and that was when we had our velocity, and that's in miles per hour, and our time here, and our velocity, let's assume is a constant 30 miles per hour. Good. Now, um, let's assume that we're moving to the right? And so, um, what is the position function looking like if we're doing that? Well, one problem is I don't know where I'm starting. So just for the sake of argument, let's suppose that we're starting at 0. Then how far have I traveled at time 0.1? Well, I would take 30 times 0.1, right? And that would be my distance traveled because I'm looking for the area. And so similarly, if I go out to a generic value at time t, right, then it's going to be the area of this rectangle, and that's 1/2 times 30 times, or sorry, 1/2. That's the triangle. Rectangle is just 30 times t. So our S of t is actually going to be 30 times t, right? And that's just going to be looking like that. So at time, at time 1, we've gone 30. And at time 2, we've gone 60. There's this nice relationship there, right? At time 3, we've gone 90. And so on. So this graph is actually telling you what the area is under this curve. Well, as it turns out, this function right here, if you differentiate this function, you get the velocity. So we note S prime of t is 30, and that's equal to the velocity. And so we say that S of t is called an antiderivative. So antiderivative of the velocity, which in this case was 30. Okay, so in general, so function f of t is an antiderivative of g of t if f prime of t is equal to g of t. Okay? And so some antiderivatives are easy to compute, some are harder. So let's just try a couple. We saw that if our velocity function is a constant, you could say miles per hour if you like, then the antiderivative, S of t, would just be our k times t, right? And that's because S prime of t then would be k. Of course, you might say, well, that's not the only function whose derivative is k, right? You could add another constant onto the end there. And so if that was a constant, right, the derivative would still be k, right? Because the derivative of any line is going to be its slope, so the intercept could be anything. So that's why we were saying we have an antiderivative, right? So our antiderivatives aren't going to be uniquely defined that way. Good. So what does that mean in terms of the graph here? If our velocity is, say, let's be specific, 30 miles per hour, why would your position function be 30t and then plus some unknown c? Well, the c here is actually telling you where you started at time 0. So notice s at time 0 is equal to c, right? So that means, right, you may be moving at 30 miles an hour, but you don't know where you've started. And so this is telling you that you're moving 30 units to the right at each time t, right? But you don't know where you started, so you'd have to add your starting position onto the end of that, right? So to figure out the full antiderivative, you would need to know that where you started. Okay, we're not going to get that far into it right now, but that's just the relationship between those. And so our first antiderivative then is that if you have a constant velocity, then your general antiderivative would be k times t plus b, where b again, I guess I use c there. Let me use a c there. And that's the starting position. Okay, so suppose that g of t now is equal to t. What would your antiderivative be? F of t. F of t is antiderivative. So I took the derivative of something and I got a t. So it seems like I would have had to have differentiated t squared, right, to get a t to the 1 power. But now if I just have a t squared here, that would be a 2t. I need to do something to get rid of the 2, and so I would need to multiply the front by 1/2 t squared. And so now my antiderivative would be 1/2 t squared. So you can check your answer pretty quickly, right? Because f prime of t then would be 1/2 times 2t to the 1 power, and so that is t. Good. And so that's an antiderivative. Good. Now, why am I bringing up antiderivatives? So in that example, we were seeing that the velocity, if you're looking through the velocity function from time A to time B, right, we know that the distance traveled, we're just going to assume that our function is positive for now. Distance traveled will be our constant, that's our 30. 30 times the length of this interval, which would be b minus a, right? Well, notice that that is the same thing if s of t is 30 times t, then the distance traveled here from time A to time B, A to time B, that's an A, is just going to be s of b minus s of a, which is 30b minus 30a, which is 30 times b minus a. And so these answers are the same then. So you could actually use the antiderivative to compute your distance traveled. But we're going to talk about that a lot more in the next section. All right, so I think I'll stop there. That'll get you through the last of the homework problems.